In this lab, caffeine taken from brewing coffee grounds was extracted from the aqueous phase into the solvent dichloromethane. The main technique utilizes extraction, which is the moving of a desired product from one solvent to another based on said product's solubility. The purpose of this experiment was to determine which variables affected the concentration of caffeine extracted into the dichloromethane phase, and how much each tested variable had an effect. We chose to look at the time of collection, the mass of coffee in the tea bags, and the number of inversions. In order to determine the amount of caffeine in the dichloromethane phase, a spectrophotometer was utilized. And knowing how to extract caffeine is important, as it is a key ingredient in food and drugs across the world. Now, moving on to theory, the main driving factor between moving the caffeine from the aqueous to the dichloromethane phase is its solubility. The solubility of caffeine in the dichloromethane phase is much higher and is driven by thermodynamics, as the molecule wants to move to a state with a lower energy. There's a liquid-liquid equilibrium that forms between these two phases, as you can see on the right, a distinct aqueous phase on the top and a distinct dichloromethane phase on the bottom due to their differences in density. The aqueous phase is caffeine poor, while the dichloromethane phase is caffeine rich. There is a diffusion between the two boundaries as well. In terms of figuring out the concentration of caffeine, the main equation involved is Buehler's law, where A is the absorbance, epsilon is the molar absorptivity coefficient, B is the path length, and C is the concentration. Using Buehler's law and a simple calibration curve, we are able to calculate the amount of caffeine in this caffeine-rich solvent.
There were several safety concerns when performing this lab. When in the lab, you should always have your personal goggles, lab coat, and safety gloves on. When handling dichloromethane in particular, which is a carcinogen and a potential mutagen, you should have silver shield gloves in addition to your purple nitrile gloves, as well as a face mask in addition to your goggles. Waste should be put in the proper containers, including the aqueous residue from the extractions. To repeat, this cannot be put down the sink. It should be put in the aqueous waste container, while the dichloromethane leftovers from the extraction should be put in the organic waste containers.
So in order to get the caffeine and coffee to enter into the liquid phase, we grinded it, and then we took the coffee grounds and we weighed them to predetermined masses. And they were placed in tea bags, stapled shut, so they could be placed into the reactor. So now looking at our reactor setup, we have a metal vessel on top of a hot plate that we use to heat 3 liters of water that will be used during the experiment. The water runs through a small plastic pipeline into a pump, where the pump pumps it into a regulator, which allows us to regulate our flow. This wasn't given at any volumetric flow, but as a numeric value, and we set our numeric value to 10, where it pumped it up another little plastic line into our reactor, which was a piece of glassware with a stopper, which allowed us to control the outlet flow, and where we were able to control the volume of DI water that was held in our reactor. And it was collected at the bottom into 15 milliliter samples in Erlenmeyer flasks.
15 milliliters of dichloromethane are added to 15 milliliters of the aqueous caffeine solution. Dichloromethane is more dense than water is, so it settles at the bottom. The cap of the separatory funnel is placed securely on before the separatory funnel is taken off of the clamp. The cap is held securely for the inversions. In this particular video, 3 inversions are done. We did 3, 5, 7, and 11 inversions. And while the funnel is still facing up, the separatory funnel is open so it can degas. Then one final inversion is done very slowly so that no mixing occurs, and the 2 separate liquid phases are allowed to separate. The separatory funnel then is placed back on the stand securely, and the bottom layer, which is the dichloromethane with the newly extracted caffeine, is decanted from the bottom into the collection beaker. 3 dichloromethane extractions on the same 15 milliliter sample of aqueous caffeine solution give the product for testing in the spectrophotometer. Put the product into the quartz cuvette and make sure that the transparent side is facing the light beam when it's loaded into the spectrophotometer. This analysis is done at 275 nanometers. The answer given is in absorbance units. This absorbance information, along with a calibration curve, can be used to determine the concentration of caffeine. We're able to do this because of Buehler's law.
Looking at our first graph, the variable that was changed was the time during the diffusion that the sample was collected, and everything else that was held constant is listed on the side of the graph. The samples were collected every minute up to 4 minutes, as the available caffeine along the outside of the coffee grounds entered into the system. The caffeine concentration increased up until 3 minutes, at which point most of the available caffeine had already entered the water, and that is why at the 4th minute the concentration decreased, thus giving the graph a parabolic trend line.
The second variable tested was the mass of coffee grounds in the tea bag. We tested 0.2, 0.4, 0.6, 0.8, and 1 gram. The trend of the data is linear between 0.2 and 0.8, with little standard deviation. There is an outlier at 1 gram, where the results are much higher than what would be expected from the trend previously established. We attribute this to an error during our experiments, as we took the 3 trials from the same tea bag. We recommend testing 0.8, 1 gram, and 1.2 grams again to verify that there is in fact a linear relationship between the variables.
One variable tested was number of inversions of the separatory funnel before decanting. The numbers tested were 3, 5, 7, and 11 inversions. The trend of the data is logarithmic. As number of inversions increased, so did the concentration of caffeine extracted. As number of inversions will increase, it'll approach an asymptote until all of the caffeine is extracted from the aqueous phase. The number of inversions had a surprisingly large effect on the concentration of caffeine extracted.
So in conclusion, with our increasing collection time, it resulted in a parabolic trend with 3 minutes being the maximum caffeine concentration, with the concentration declining in the minutes to come. Then, with the mass, it was a fairly linear trend except for the outlier at 1 gram, which can be confirmed with multiple trials. For inversions, they follow a logarithmic trend, which can be verified by doing more tests to see the asymptote.